the presentation number should be 557.
Yeah. Yeah, it's loading. That's why it takes some time. Thanks for your introduction. I'm Sergio Blasón. I am working as a postdoc researcher at the BAM Institute, and this work has been completed thanks to the help of our colleagues from Mondragon University in Basque Country in Spain. And well, I would prefer to skip the outline because otherwise I am always out of the time. So basically the framework of this research project is based on the lack of some regulation in order to evaluate the structural integrity of vessels. You know that when we are using additive manufacturing techniques, still up to now there are no clear idea about the behavior of the materials, and that's why we are interested in developing this project. In this case, we are taking into account the steel 316L, so it's the same that used in the previous presentation. And in general, the general aim of this project is basically to develop a design concept of additive manufacturing components in order to identify the most risky areas inside of the component, and from that point try to evaluate the lifetime of the material, of the component in general. Probably all of us are familiar with the benefits and drawbacks of this kind of materials. We know that there are a lot of benefits in terms of the complex geometry, flexibility and so on, but we cannot avoid the uncertainty in terms of the mechanical properties, basically due to mainly to the difference in the thermal history along the process. And of course, we need to consider the presence of defects that is not possible to avoid, at least up to now. And this makes also, or produce also, different distribution of the residual stresses, which should be taken into account. I would like to mention that BAM Institute, from the last 2 months or something like that, has founded a competence center on additive manufacturing, and the aim is try to speed up the evaluation of risky components in order to try to use different components in relevant applications. BAM has a lot of different departments working on different areas. That's why we work with different materials, metals, ceramics, concrete. And since we are an interdisciplinary institution, we have identified different work pages, but in this case the framework of my presentation is involved according to the image tolerance design. Sorry. Okay. So this is the main idea of the methodology that we are proposing. First of all, we want to identify using simulations the most risky area in the component. And from that point, we are going to identify the evolution of the temperature along the process, the manufacturing process. From that point, we want to check the performance of the material by doing, in this case, curve propagation tests and also high cycle fatigue tests. So basically, we are interested in this case in fatigue properties. And from that point, we want to reproduce some kind of representative specimens, which means that we want to reproduce the same behavior of the original component, but not using the specimen extracted directly from the component, but specimens produced ad hoc. And from that point, we want to check the fatigue performance of the material. So this is the archetype that we are using nowadays. It's a vessel of 316 steel, and the heat treatment was this one, 5 hours under 560 degrees, and basically you can see different areas in the component. Oops, 3 main areas. The cylindrical part, which can be divided in 2 different because we have different thickness, and also the cone, which means that the building direction compared with the direction of the specimens are different in each place, and we want to check the performance in each position. So basically, once again, I am repeating a little bit, but we want to compare the behavior of the original component, extracting different specimens and trying to characterize the fatigue response, and then we want to produce some representative specimens, which means that we are reproducing specimens but without extracting directly from the component, and then we want to check the transferability between both sample of results and try to get a good correspondence. Okay, there are another division at BAM working in the numerical modeling, and these results are starting from that department, but it's easy to see that the most affected zone in terms of the temperature is the cone, because it's easy to see that the time between each layer is lower, so it's easy to see that the temperature should be higher in the cone region. And we will see some results connected with this fact. Apart from that, since we are basically trying to zoning the component, zoning means basically, under our perspective, try to identify the most risky area around the component. We are trying to collect as many specimens as possible in order to see any risky area, or which we can say the weakest area of the component. That's why we are trying to collect many specimens. We can see the round ones, which corresponds to the high cycle fatigue specimens, and the rectangular ones, which are used to complete the fatigue drag propagation test. According to this, for each vessel, we are collecting in total 58 specimens, so we have a lot of information to characterize. And I will show you the main results up to now. I should mention that up to now we don't have the whole results, just a preliminary ones. In any case, according to the fatigue drag rate curves, we are defining a reference plane, which coincides with this one, and we are trying to characterize different positions along the circumferential direction in order to see if there are different responses depending on the position. And you can see here the three regions that I mentioned before. The lower part of the thickness, of the cylindrical part, sorry, which has 15 millimeters thickness, the upper part, which is 11 millimeter thickness, and the cone part, which has 45 degrees of tilt regarding the building direction. And according to the fatigue drag test, we are doing this methodology, this procedure. First of all, we are going down in order to characterize the threshold regime and also the near threshold regime. And then, if we have enough ligament, we go up in order to characterize the Paris regime. In all the cases, we are using the log ratio equal to 0.1. We use this kind of chevron notch in order to avoid any kind of non-symmetrical evolution, because we had some bad experience using the straight notch in the past. Also, I would like to mention that we are using 3 millimeters thickness. And first of all, I would like to show you the images of the surface, the fracture surface, because especially in the case of the 0 degrees, we can see some effects probably due to the residual stresses. And it's easy to see these effects when we compare the results from the different points that we are evaluating. And for example, if we compare the 0 degrees against the rest of the position, we can see clearly some kind of effect, probably due to the residual stresses. Also, some important highlight is that when we compare the behavior of the material on different positions in terms of the thickness, we can see differences, because there is some kind of mismatch under the same loading conditions. So that basically let us know that it's difficult to manage this kind of materials. In any case, when we compare all the results obtained from the 3 different regions, we can see especially that in the cone is the weakest area, because under the same loading condition we have a higher drag propagation rate, and also the threshold value is lower than in the rest of the case. And also it's important to mention that even though the scatter in the rest of the specimens is more or less in agreement with this kind of additive manufacturing components, there are some particular direction, both in the upper and in the lower region, that seems to be weakest than the rest of the specimens, probably due to the flux direction. And according to the high cycle fatigue testing, we only have collected specimens from the upper part of the cylindrical part of the vessel, and when we compare the number of cycles for different positions, here we are using always the same stress range, because we are not able to define the SM field, and also because we want to identify some kind of differences in terms of behavior comparing different positions. So when we do something like this, we cannot identify any particular difference, but something which is also very well known, when we take a look to the surface, fracture surface, we can see the magnitude of the defects, and in some of the cases are really huge. For example, in this one, which is almost half millimeter length here. And when we use, instead of the stress range versus the number of cycles, which is the typical representation for the SM field, we use the defect size, in this case the root square of the defect size against the number of cycles, we can see a clear dependence of the lifetime with the defect area. So this is in agreement with many results, and probably this let us know that the short crack regime is practically new in this case, and we are always working with propagation stage. So, as a summary, we can say that the thermal histories during the manufacturing plays an important role in order to characterize the materials, and also because the residual stresses in different positions makes it difficult to have a general idea of the behavior of the material. So that's why we think that it's very important to zone in the component in order to evaluate the most risky area. And apart from that, it's clear that in terms of the high cycle fatigue results, there are a clear dependence between the lifetimes of the defect sites. So, but in any case, from this point, we have a lot of experimental work to do, and I hope that in the next conference we can share with you all these results. So, thanks for your attention, and if you have any questions, please let me know.
Thank you for the very nice presentation. Any question from the audience? Yes, please.
So the residual stress. So when you cut out this specimen from your, suppose that you relieve the residual stress. So on your test data, there shouldn't be much of an effect of the residual stress.
Yeah. Are you referring to the fatigue graph test?
Yes.
Yeah. Because we have measured, in this case, in the high cycle fatigue test, we have information about the residual stress on the surface, and we have removed the surface layers in order to minimize those effects. But it's true that in the case of the fatigue rate test, we have no information about the real condition. So, in fact, we think that probably these results, according to the cone part, is because the effective load ratio is much higher than the expected one. So, in principle, we are working under 0.1, but probably in this case, there are no closure effects. So, we assume that that is the reason, but we need to check.
Okay. Yes, please.
Thank you for your presentation. Which criteria will determine the criticality of the regions of the part?
Well, in this case, this is the criteria. I mean, we can clearly see that the cone part, the response of the cone part is much worse than the rest of the ones. So that's why we define the cone part as the most critical region. So basically, we are evaluating many different positions in order to see which one is the worst one. I don't know if I am answering you, but that's the only.
Last question.
Yeah, as I understood, you associated this worst region of fatigue crack growth with residual stress.
Yeah.
Yeah,
I think so. In fact, if you can see here, the scatter in the upper and lower part, let's say, is huge compared with the usual response of conventional materials, but in the case of the cone, the scatter is much lower. So we assume that due to the higher load ratio effective condition, we assume that this is the reason because the scatter is much lower. So basically, we think that here we are working under crack closure free effects.
So, thank you very much again.
Okay, we can